So Dr. Julie McEnery is a preeminent high-energy astrophysicist. She did her undergraduate studies at University of Manchester and started working in the area of gamma-ray astronomy as a graduate student at University of College Dublin, working on the Whipple telescope, one of the first ground-based gamma-ray telescopes operated in Arizona in conjunction with the Smithsonian Astronomical Observatory. After she completed her PhD, she worked as a postdoc on the Milagro experiment with a couple NYU physics professors as well, Alan Mintzer and Peter Nemeth. After completing her postdoc at Milagro, she moved to NASA Goddard Space Flight Center, where she is now the Fermi project scientist of the Fermi Gamma-ray Space Telescope, as well as co-director of the Joint Space Sciences Institute, institution with NASA Goddard Space Flight Center and University of Maryland. So without further ado, Dr. Julie McEnery.
Good evening, everyone, and thanks, Yossi, for that nice introduction. So this evening, I'm going to describe to you some of the more interesting things that we've discovered in the last 4.5 years with the Fermi Gamma-ray Space Telescope. The Fermi Gamma-ray Space Telescope is that spacecraft that you see superimposed on top of our 4-year sky map. But I'd like to start more simply. If you look at the sky at night, you see stars. And if the time of the month is right, you see the moon. And if you know where to look, you can see planets moving slowly through the sky. On this image, that bright object in the center is Jupiter. If you're in a really dark place, you can see the faint glow of our Milky Way galaxy. This is the optical universe that mankind has been studying for millennia, from the Babylonians right up to the modern day. But I want to address a different question. What if you had gamma-ray vision? This is one better than Superman, who only had X-ray vision. Gamma-rays are just a little bit more energetic. So if you had gamma-ray eyes, you'd see nothing at all. And the reason for that is that the Earth's atmosphere absorbs gamma rays. And that's why, if we want to view the gamma-ray universe, we have to take some kind of detector and put it outside the Earth's atmosphere. So let me tell you a little bit more about gamma rays. What's shown here is the electromagnetic spectrum. That's a fancy way of saying that there are many different forms of light, and that as I start at low energies with radio, those low energies and long wavelengths with radio, and I increase the energy, I go to microwaves, and I increase the energy again, I go to infrared, and then to visible radiation, and then to X-ray, and finally to gamma-ray. Gamma-ray is the most energetic. Now you're familiar, all of these are the same phenomenon, but you're most familiar with visible light because that's what your eyes can see. But when you're viewing the world, you're only sampling a very small fraction of the electromagnetic spectrum. There's so much more to the universe than you can see with your eyes. The instrument I work on, Fermi, covers this much larger swath of the electromagnetic spectrum to much higher energies. Now, gamma-ray is the most energetic form of light, and that's exciting because it's produced in the most extreme places in the universe. You don't produce a gamma-ray in a gently shining star. You produce them in stars that are exploding. You produce them in places where matter is being sucked onto a supermassive black hole. Personally, I feel that it touches and pulls out all of the exciting parts of astrophysics because you eliminate all of those boring sources that just shine gently and quietly. But coming back to a reason to look across the electromagnetic spectrum, just to give you an illustration of why this is important, in this image, what you see is a hand holding an iPhone in infrared, in visible, in ultraviolet, and in X-ray. And what you can see that as you view the same object in different parts of the electromagnetic spectrum, you get to see new information, new things. So what I want to do in the remainder of this talk is tell you what we've uncovered when we view the universe with gamma-ray eyes, when we view the universe at the highest possible energies. So what do we see when we make a map of the gamma-ray universe, which we can do because we have a spacecraft that is in orbit around our Earth. It is drastically different to the optical universe that you're familiar with. This map is a map in galactic coordinates. And what that means is that the center, that our galaxy, our Milky Way, is that swath across the center. So the thing that when you see the sky with your eyes and you see a faint glow of the Milky Way, in gamma rays, if you had gamma ray vision, that Milky Way would be blazingly bright. Over 80% of the gamma rays that we see are produced in the Milky Way galaxy. And they're produced when particles, charged particles that are moving close to the speed of light, slam into gas and radiation in our galaxy, and in that interaction produce gamma rays. In the gamma ray sky, there's no night and day. Gamma rays are one of the few wavelengths where the moon is brighter than the sun, and neither are bright, particularly. If I was the sun and the moon are both in this image, but in fact, the sun is less bright than some active galaxies, than some pulsars, and I'll describe those in a moment. Okay. You also can see that in addition to this swath across the center of the sky, there's points of gamma rays. And some of those are things known as pulsars. These are super dense stars that are spinning rapidly and have huge magnetic fields, huge electric fields, and produce a large amount of very high energy radiation. We see them pulsing as a beam of radiation sweeps across our line of sight several times a second. If you take a supermassive black hole and you put it at the center of a galaxy and suck material into it, in some fraction of the time, that system will produce a jet of particles that are moving close to the speed of light. And in some fraction of those objects, that jet is pointing directly at us, beaming the radiation from those particles that are moving close to the speed of light right at us. These objects are enormously bright. They exist close to the edge of the universe, but they are, for us, one of the brightest things in the sky. We also see that they're very, very variable. The amount of gamma rays that we see per hour can change sometimes by as much as a factor of 100 in a day. And what that's telling us is the nature of changes in accretion onto that central supermassive black hole. We have gamma ray bursts. These are extreme exploding stars or merging black holes and neutron stars. These are the brightest explosions we know of since the Big Bang itself, and I'll describe a little about these later in my talk. And then we have the unknown. Lots of objects in the gamma ray sky remain mysterious. We know that something exciting is there. We can see that there's a gamma ray source, but we don't know what it is. There's a lot of discovery. We've been doing optical astronomy for several thousand years. Gamma ray astronomy is really a 21st century experience, and we're only just learning what the gamma ray sky looks like. So as a consequence, there's lots of objects in the gamma ray sky that we don't know what they are. There's other things in the sky that I haven't described. We see gamma rays from black hole or a pulsar orbiting around a massive star. We see gamma rays from supernova remnants, the remnants of a massive star that has exploded at the end of its life. Okay, so if your eyes can't see gamma rays, we need to build some kind of a detector that can. This is one of these places where Einstein comes to the rescue. His famous equation, E equals mc squared, actually matters here. In this equation, E is energy, m is mass, and c is the speed of light in a vacuum. And what this equation is telling us is that I can take pure energy, like a gamma ray, and in the right conditions, convert it to mass, which is m in this equation. Now, since the speed of light is a very, very large number, I need to have a very large amount of energy to produce matter. But I have a very large amount of energy because I've just told you that gamma rays are the most energetic form of light. So what we do to make our detection. This is a schematic of the instrument. An incoming gamma ray comes in. In our detector, it interacts to produce an electron and the antimatter particle to the electron, the positron. And these pair of particles move through the detector. In the top part, in this blowout, we have tracking devices that track precisely the location of the electron and positron pair. At the bottom, we have a very heavy detector that catches all of the energy produced in the interaction and tells us the energy of the gamma ray. So we can, from both of these two, we can figure out both where the gamma ray came from and how much energy it has. And we detect gamma rays one gamma ray at a time, one photon at a time. We surround the entire instrument with a shield that will fire if it sees a charged particle, but will not fire if it sees a gamma ray. And that's because the environment in space contains a very large number of charged particles, and if we didn't have this kind of shield, we would find that we were completely swamped by background. We see about 10,000 charged particles for every gamma ray that we detect in our detector. What I'd like to do here is show an animation of the detector working. We're sweeping into the instrument. This is the gamma ray coming in. It's converted to an electron-positron pair. You can see that the detectors are lighting up, indicating the position-sensitive detectors. It now reconstructs back, and we can use this to tell where the gamma ray comes from. The main instrument is called the Large Area Telescope, and it's an international effort. We have a collaboration between Japan, Italy, Sweden, France, and Germany. The key part of this instrument is the tracker, the place where the electron and positron positions are measured very precisely. This part of the instrument is about 70 square meters of silicon. So just to put this into context, this would make about 1 million digital cameras. At the time that it was built, it was the largest silicon detector ever built. It's since been, larger ones have been built as part of the particle accelerators in CERN. But something that we did that they didn't have to do is put it on a rocket and send it into space. We read out about 1 million channels of information. So this is a picture of the various components of the instrument, and I'm showing it here in part that my background is as an experimentalist. So to me, this is like my baby in its early stages. So some fun facts. I mentioned that at the time that it was built, the LAT was the largest silicon detector in the world, with enough silicon to make almost 1 million digital cameras. We collect information from 1 million different sensors, several thousand times a second. And we power this with the equivalent of a hairdryer. It's 650 watts. And that 650 watts is powered entirely by solar energy. We read out the data and send it to the ground on what is the equivalent of the average of a dial-up connection. So working in space means the development of low power usage electronics, low power usage equipment, and very efficient data compression and data storage. And the energy range of Fermi is so large that if the instruments were a piano, it would cover 23 octaves. So we're covering a huge fraction of the electromagnetic spectrum. I mean, we're not only opening our eyes, we're opening our eyes wide. So having an instrument is not by itself sufficient to study the sky. You need to put it on a spacecraft that can provide power, communications, dissipate heat, tell you where you're looking. So this is the spacecraft when it was during assembly in Arizona. Standing in front of there are a few of my colleagues. This was during a major review. This photograph was taken just before we added the solar panels, so the 4 connectors that you see there ultimately will have a connection to the solar panels, and what you're seeing is the radiator that we use to dissipate heat. You also need to get the spacecraft into low Earth orbit. So here's a picture of the spacecraft a few weeks before launch. Now the spacecraft has been placed on top of the rocket. What you see at the bottom of this image is the second stage of the rocket. Below, you were at this photograph, were 11 stories off the ground. The other 10 stories are what will be a large receptacle carrying a huge amount of flammable liquid and explosives, which, if you've spent several years working very hard to develop an instrument, makes you a little nervous. So you can see the large area telescope is the box at the top. There's a second instrument, the gamma ray burst monitor, which is that collection of white boxes that you see. In this photograph, we see one half of the fairing. After launch, the two parts split open, and eventually the spacecraft is sent by itself into space. And this is just some photographs a week before launch, where we're now making the finishing touches. And here's me with some of my deputies. So the night before launch is a time lots of people took this photograph because most of us couldn't sleep. And again, it's largely because your instrument is a tiny little thing in the top of this very large rocket, and this is the most likely place for something really bad to happen. So this is a picture of launch. We launched from Cape Canaveral on the 11th of June 2008, aiming for a circular orbit, 565 kilometers altitude. Now, to understand the next slide, I need to tell you that for people watching remotely, the video feed was delayed by a couple of seconds from the audio feed. So people who were sitting in the Mission Operations Center at Goddard Space Flight Center, which is where I work, heard the countdown. 3, 2, 1, we have liftoff, and they saw absolutely nothing. And then the next thing that they saw was this. Now, what's actually happening here is during a launch, a large amount of water is flowed across the bottom of the launch pad so that the act of launching doesn't destroy the launch pad that you've launched from, because you want to be able to reuse the pad. So this is actually steam. It's not the rocket blowing up. And this moment of agony only lasted a couple of seconds, but I'm told it felt like an eternity. And then we headed off into outer space. So we've been operating very well since that time. But occasionally excitements happen. So in April this year, we're happily bumbling around our orbit when an obsolete Soviet satellite came right across where we were going to be. The two orbits were almost exactly intersecting. And they were predicted, the two orbits were intersecting. They were predicted to the two spacecraft were predicted to be within about 200 meters of each other. Now they're moving at a relative velocity of 12 kilometers per second. So another way of stating this is that the Air Force monitoring was telling us that they expected that both spacecraft would occupy exactly the same point in space, 50 milliseconds apart. So that's a little bit nerve-wracking. So in the game of chicken between us and the Soviet spacecraft, we moved out of the way. And this was the first time that we've used our propulsion system, so it was quite an exciting engineering feat. It just takes a second because we've got a very overpowered propulsion system, but it was the most stressful second that I've encountered in all of 2012. Okay, so let me move on to some observations, the kinds of things that we have seen in the sky. So we're back to the Fermi sky, and if you've got excellent eyesight, you may notice that there's a faint evidence of an excess below and above the galactic center. And if you don't believe me, let me show you some image processing to enhance that feature. So we smooth the map, and then you stretch the contrast. Then you mask out those point sources because we're interested in a large feature. And then finally, we subtract out the diffuse emission, the emission produced by the relativistic particles smashing into the gas and radiation fields. And what you're left with is this ghost of an image of these large bubbles above and below the galactic plane. This is really a stunning result because this is one of the largest features that we know about in our galaxy. And we didn't know about it until the observations by Fermi a couple of years ago. The structures go for about 25,000 light years north and 25,000 light years south of the galactic plane, extending 50,000 light years in total. Our entire galaxy from one end to the other is 100,000 light years. So this is one of the largest structures in our galaxy. If we look at the distribution of the energies of these gamma rays, how many gamma rays we get at various different energies, we find that there's an unusually large number of high energy gamma rays. And this is telling us that there must be an unusually large number of high energy particles occupying that region of space. We also see that the edge of these bubbles are very sharp. So this isn't something fluffy just being generated in place. It's more like something happened a few million years ago at the center of our galaxy to inject a huge amount of energy, and that's what we're seeing is the remnants of that expanding out into the intergalactic medium. So this is an artist's impression to give you a better picture of how this looks like relative to an optical image of the Milky Way galaxy that you might be more familiar with. If you were to tip this structure on its side, the bubbles would reach far enough to include the solar system. Really huge. So why are these so mysterious? Well, we know that the center of our galaxy hosts a black hole with 3 to 4 million times the sun's mass. We don't see any evidence that the black hole in our galaxy is active or is producing a large amount of radiation. But we know that other galaxies do. So perhaps at some point in the past, our galaxy was active. Our galaxy had the kinds of jets that I spoke about right at the beginning of this talk. Or perhaps we had a burst of star formation where a very large number of stars all formed at the same time, all pouring a large amount of radiation and energy into the environment. Or maybe we had both. Some star formation to kick off the structure and then later activity to keep it energized, to keep those particles bright. But whatever it is, this is very strong evidence of the activity of previous generations in the center of our galaxy. Okay, I haven't described to you how we operate. Our instrument sees about 20% of the sky at any instant. So if you imagine we were pointed directly away from the Earth and swept around, what you'd have is you'd cover the entire sky, but you'd have a little hole in the north and a little hole in the south. And we don't want that. So instead, we tip north for one orbit by 50 degrees and north for the second orbit by 50 degrees. And every 2 orbits, we cover the entire sky. This gives us enormous discovery potential because now we're not only exploring the sky at a new wavelength, at new energies, we're also exploring the sky at new timescales. We're able to see how the sky evolves in time. We can catch rare events. We can see how the gamma ray sky evolves with time. On the bottom, I show how we fill the sky every 2 orbits. So this is just simply repeating and showing that every 2 orbits we see the entire sky. But of course, this allows us to make a movie. So you spot the moving source there. I'll come back to that in a moment. So what I've done here is I take the top galactic hemisphere and the bottom galactic hemisphere, and I've made a movie where each frame in this movie is 1 day. And what you can see are these individual points are getting brighter and dimmer. Those are the active galaxies. Changing amounts of accretion at the supermassive black hole is powering huge changes in the gamma rays that we see. The object that's running around, I don't know where there it is, it's up at the top, is the sun. I did tell you that the moon is brighter than the sun, but because the moon appears to move so quickly through this sky, you can't actually see it in an animation made on day-long timescales. But the emission from the sun is produced when these charged particles, the same ones that produce the emission in our galaxy, interact with optical light from the sun and produce gamma rays in that interaction. So it's not really being produced by the sun itself. Okay, so let's go and blow some things up. So to put things into context, the Earth is really small compared to the Sun. So there's the Sun, and for reference, I show to scale the Moon and the Earth. And the reason that I do this is that I want you to imagine taking the mass of the Sun, in fact it's taking a little bit more than the mass of the Sun, and compressing it so that it fits within the size of Abu Dhabi Island. What you're essentially creating is a very, very large nucleus. It's incredibly heavy. One teaspoon will weigh as much as a whole mountain. And when you're compressing the matter, you're also compressing and enhancing the magnetic field. So we've got magnetic fields that are 1 million times greater than any magnetic fields that we can produce here on Earth. Those magnetic fields induce electric fields. So we have enormously high electric fields. We've got enormously high gravitational fields. The entire system is spinning rapidly. The way angular momentum behaves, that if you take a large, slowly rotating object and compress it so that it's a small object, to conserve angular momentum, it's going to spin more quickly. So the system is spinning very rapidly. So this is an enormously extreme environment. Electrons are accelerated by these electric fields. The entire system is rotating, and this gives us pulses of gamma rays. And to give you a sense of how quick some of them move, thinking of something the size of Abu Dhabi Island that has the mass of the Sun, rotating as fast as a ceiling fan is a reasonable image to bear in your mind. So how do you produce these? Well, they're produced in a stellar explosion at the end of a star's life. As it runs out of fuel, material collapses and heats up and induces new nuclear reactions. And when the new nuclear fuels burn, it collapses more. And what you're seeing is the induction of different nuclear processes until eventually it can't do any more. Everything collapses down and you have a large explosion. And the compression in that explosion leaves behind the neutron star at the center. Pulsars are what's left. These rotating neutron stars are known as pulsars. And they have been one of the most exciting discoveries of Fermi. So this is a subset, the first few pulsars that we saw. We now have over 120. These pulsars are amazing. And the reason that they're amazing is a third of the pulsars that you see in this sky are detected only in gamma rays. That prior to the launch of Fermi, we weren't able to see most of the pulsars that were out there. So the number of pulsars that are in the sky is much, much greater than we had previously thought, because so many of them are radiating only at gamma ray energies. In this image, it's a masterpiece of PowerPoint manipulation that was not done by me. The images are flickering at a rate that is 1/10 of the true pulsation rate of the pulsar. And you can see that there's different colors. So the yellow are pulsars that are discovered using the Fermi data alone. The blue dots are the regular pulsars, the common or garden pulsars that we knew about from radio observations. And the little pink ones that are doing their nut, those are millisecond pulsars. They are spinning extremely rapidly because at one point in their evolution, they accreted material from a nearby star, a little bit like spinning up a top, and got respun up. In this sky, before we launched Fermi, we expected to see radio pulsars. We hoped we might see pulsars in a blind search, and we were stunned to discover so many millisecond pulsars in the sky. You'll also notice that the millisecond pulsars, while most of the pulsars appear to lie along our galaxy, which is what you would expect, because pulsars are a member of our galaxy, the millisecond pulsars are not. And that's because millisecond pulsars, we can only see the ones that are closest to us. So they don't appear to look in the galaxy because we're seeing things that are only close by to us, so they have a more isotropic distribution. I suppose I should have done that animation. Okay, so now I'd like to move on to another kind of explosion, gamma ray bursts. The left-hand side shows a map of the sky for the 10 seconds of this gamma ray burst. During this gamma ray burst, the gamma ray burst is by far the brightest object in the gamma ray sky. Observations over the last decade have shown us that gamma ray bursts are at very large distances from us. They aren't in our galaxy. They're much further away, closer to the edge of the universe. So if you take something that's very bright, and now you say it's also very far away, it means that intrinsically it's enormously energetic. These are the largest explosions that we know of since the Big Bang. In a few seconds, these objects are releasing an amount of energy that is equivalent to something like a rest mass of the sun being converted entirely to energy. So we're not talking about just a measly electron and positron. Now it's an entire star. So what kind of things can produce this? One suggestion is that you take two neutron stars or a neutron star and a black hole, and they collide. And in the collision, produce a jet of relativistic particles that's responsible for producing the gamma ray burst. In the process, you're witnessing the birth of a black hole. A second possibility is a collapsar. You take a very, very large star with a rapidly spinning central core, and it collapses, and it produces a supernova. But this is a special supernova. It's an especially energetic one, and one that has a large amount of rotation. And it also produces a jet. But in this case, we also see evidence of a supernova. And we have suggestions for gamma ray bursts that, in fact, we're seeing both of these, evidence for both of these phenomena in our data. With Fermi, we've detected the most energetic gamma ray burst yet. We've seen the highest energy emission from a gamma ray burst. So we're learning entirely new things about what's happening in the jet of a gamma ray burst. But I'd like to focus on another use of these. And this is coming back to Einstein. One of Einstein's fundamental theories is the theory of special relativity, where he postulated that the speed of light is fixed. It's a constant in a vacuum. But you don't want to just believe Einstein. It's always good to test these things. And in particular, it's interesting to test whether Einstein is correct, because if we want to try and find physical models that unify quantum mechanics and gravity, in many cases, this allows for a situation where the universe, the vacuum in a universe, is not just empty. It actually has a foamy structure of space-time. And the very high energy that we have for gamma rays implies a very small wavelength, a wavelength small enough that the gamma rays might actually see the structure of space-time. So if you imagine two things going down a rocky road, one is a large SUV, and the other is an ant. They're both going down the same road, but the ant has to go up and down and up and down and up and down all the little bumps, and the SUV doesn't even see them. It just goes marching straight along. That's the image you should take on the difference between how a low-energy photon and a high-energy photon might go through a foamy space-time. So you'd expect the high-energy gamma rays to be delayed with respect to the low-energy gamma rays. We find that gamma ray bursts are an excellent test of this, because how do you test it? What you want is to set up a race, and you want the race to start very, very far away. You want a very long race. And you want to have a good starting clock, so you need to have an explosion. A gamma ray burst is perfect, because it just goes bang, and before the gamma ray burst, there was no emission, and it's over very quickly. So this is an example of a gamma ray burst on the left-hand side. The details are actually not that important. What you're seeing is time on the x-axis and counts on the y-axis. In this burst, the highest energy gamma ray arrived within 0.9 seconds of the lower energy photons. This is while the burst is still going on, so it's in time. This is after traveling 7 billion years. This allowed us to say that the speed of light at high gamma ray energies was so close to the speed of light at lower energies that we eliminate those theories of quantum gravity that predicted that space-time is foamy enough to interfere strongly with light. So we're able to use our observations to constrain something that's very difficult to constrain, which is models of string theory. Okay, so I'd now like to change gears drastically. So as the slide suggests, we're coming back to Earth. Our observatory, one of the instruments, the gamma-ray burst monitor, sees the entire sky. So looking out, it sees the sky, but it also constantly looks down and can see the Earth. And thunderstorms, while in an astrophysical sense they're not as dramatic as a supermassive black hole in another galaxy, but they are right here, very close. When we travel around the Earth, we notice that we get very, very short flashes of gamma rays. These last just milliseconds. And the spacecraft is over regions of high thunderstorm activity when we see these flashes of gamma rays. They're concentrated in the tropics near thunderstorms, and a handful of them show very unusual properties. So this is a schematic of one of the terrestrial gamma-ray flashes that we saw. The spacecraft was over Egypt at the time and detected a terrestrial gamma-ray flash, but it was an unusual one. On the left-hand side, you see a light curve. So this is time on the x-axis and counts on the y-axis, and it's unusually long, and it seems to have two peaks. But the most puzzling thing is that in Egypt at the time there were no thunderstorms. However, in Tanzania, there was a very, very large amount of thunderstorm activity. And if you look at the magnetic field lines of the Earth, you'll notice, or somebody else noticed, I didn't actually notice this, but it was noticed, that the magnetic field line that connects Tanzania travels up through Egypt, through where the spacecraft was. So while we weren't over that region of thunderstorm, we were magnetically connected. Another puzzling thing about this was the energy spectra, shown on the right-hand side here. This is energy along the x-axis, and the number of counts at each energy along the y-axis. And there's a very special feature in this plot. And that feature is a peak at 511 kiloelectron volts. Kiloelectron volts is about 1,000 times more energetic than optical light. To produce that kind of peak, what you're seeing are positrons, the antimatter particle to the electron, annihilating to produce a line of gamma ray energies that is related to the mass of the electron and positron. So this was conclusive evidence that what we were seeing were not gamma rays directly. What we were seeing was antimatter directly striking our instrument, and that temporally that antimatter is related to a thunderstorm that's happening several thousand miles away. What do we think is happening? A large amount of acceleration happens in the, I don't know if this is going to automatically play. You have a large amount of acceleration happening in the thunderstorm. These are accelerating electrons and positrons that are smashing into molecules in the atmosphere and interacting to produce gamma rays. So let's just play this. The gamma rays can spread everywhere, but the charged particles, the electrons and positrons, are constrained to follow magnetic field lines. Charged particles will follow the magnetic field. So while the gamma rays just spray off everywhere, the charged particles are staying in a small clump and are all heading out together. In the next animation, you see the spacecraft. The charged particles come through, they interact in the spacecraft, producing gamma rays all at the same energy. As the particles travel through, they hit the conjugate point, they reverse, they bounce back, they hit us twice. So we get hit twice by the same population of particles from this thunderstorm. I find it really remarkable that you can be thousands of miles away from a thunderstorm and still see such dramatic effects. So I'm almost at my last slide. What I've hoped to convey is that there's so much more to the universe than we can see with our eyes. Much, much more. And that with Fermi has provided us with a new way to view the universe, and we've discovered very dramatic new things in the last few years with our new instrument. The gamma-ray sky is constantly changing. Each day we find something new. It's constantly variable. There's an awful lot of things that I didn't discuss. I didn't tell you that we've seen the highest energy solar flare. I didn't tell you that we discovered gamma rays from a stellar nova. I didn't tell you about our ability to make very precise measurements of dark matter. There's a lot that I couldn't cover, but I hope I've conveyed to you some of the flavor of why I go to work every day. On my final slide is an animation that my graduate student made. She took a gamma ray burst and put it to music. So what you're seeing is at the beginning of this gamma ray burst, there's just a few photons. It's all kind of quiet. The main emission is 10 seconds after the start of this gamma ray burst. The colors refer to different qualities of gamma rays in our detector. The pitch is related to the energy of those gamma rays. So as we approach the main peak of this emission, the music becomes a little bit more intense. And this is the main part of the gamma ray itself. During this main peak is when most of the high energy photons arrive. That's a consistent property. I won't try and speak over it. One of our key discoveries has been that the highest energy photons in gamma ray bursts always arrive late, always arrive well after the onset of the burst at lower energies. It's one of the key discoveries of the mission. And the rest of this burst then just continues at a fairly gentle pace to the end. And that is all I wanted to say. I'd be happy to take questions.
Is brighter with respect to gamma rays than the sun. What's the reason for that?
The reason, so the way to produce gamma rays for the sun and the moon are both the same. And the sun and the moon both subtend the same angular extent on the sky. So in principle, you would imagine that they should be the same. And this emission is produced when charged particles smash into the surface of the sun and the moon. But the sun has a magnetic field. So that magnetic field diverts some of the charged particles away from the surface of the sun. And the moon does not have a magnetic field. So all of these charged particles get to smash into it. So as a result, the moon is brighter than the sun.
My question is, did this study or what you are doing right now involve any kind of dose measurements from these kind of gammas? The ones that reached at least the Earth, because this has part of the contribution to the cosmic rays that enters the Earth, and then it also contributed to the amount of background radiation that we measure, for population. I just wonder if this has any kind of involvement in these kind of those measurements, or it's not exactly the subject.
So that's a very interesting question. So I'd first like to comment on the first part. You're correct that there's a very strong connection between the kinds of detectors that we build and instruments in medical physics, and it's quite common for physicists to move between the two fields because we're dealing with the same physical processes, and the nature of the detectors, there are different applications, but the nature of the detectors is fundamentally very, very similar. So it's a place where what we do can help medical physics. On your question on what can we say something in Fermi about radiation dissymmetry and radiation levels at Earth? We do measure, we have a way to measure cosmic rays directly. And that can be related to what you will see on Earth, but in a fairly indirect way. It's generally better to use an instrument that's specifically designed to measure charged particles and monitor those as a function of time to get a sense of how radiation levels might change here on Earth. You didn't ask, but I'll mention it. The terrestrial gamma-ray flashes that showed the populations of electrons and positrons. Of course, if you were in an aeroplane, the aeroplane could just as easily be in the path of those electrons and positrons as our spacecraft was. And in that kind of a situation, the people on the plane would be temporarily irradiated by that pulse of radiation. It's sufficiently brief, and there's enough shielding in an aeroplane that it wouldn't cause lasting harm. But one of the first things that came to our mind when we discovered this was what might potential impacts be on airline travel.
If you are projecting the future, and let's talk about Nobel Prizes, anything here that is a potential for one, or anything that...
There isn't in anything I presented, but there is in a result I didn't present. I mentioned on my last slide that I haven't discussed what Fermi can do in measuring dark matter. As many of you may know, the universe is largely made up of material that we can't see and don't directly interact with. This so-called dark matter, one of the most common explanations for what it might be, which we can see the gravitational effects, we just don't see any other effects. One of the most common explanations for what it might be is a kind of particle that doesn't interact very much. So you can see its gravitational effects, but there are very, very little else. The particle physics predictions for the properties of these particles is that they should annihilate with themselves to produce gamma rays. And those gamma rays are expected to be at the energies that we can observe with Fermi. So it's possible that Fermi might be able to directly detect dark matter in our galaxy, and in fact in any place where dark matter happens to be. At the moment, we have a tentative result, it's not yet confirmed, of some evidence for seeing dark matter annihilation at the center of our galaxy. What we see is a gamma ray line at 130 giga-electron volts, which is impossible to produce in any astrophysical scenario. It's still possible that there's some aspect of our detector that we don't understand, but if this result gets confirmed, we would be identifying the nature of dark matter, we would be identifying the particle that's responsible for dark matter, and it would be, without question, I don't know if it's a Nobel Prize, but it certainly would be the most important result of the Fermi mission, because we would solve a very long-lasting question of astrophysics.
Well, when you set out Fermi, was there a set course that you set it out on? What's the likelihood that it was to intercept with the Russian? I mean, and what's to stop anything else from intercepting it? That's more random.
Generally, the way when you launch a spacecraft, it's the details of how it propagates with time are sensitive to things like how much solar activity you have, because that determines how expanded our atmosphere is, which in turn affects how much drag is seen by the spacecraft. So we can't accurately predict where our spacecraft is going to be more than about 7 days into the future. So when we launch, the orbit people make calculations of where we're launching into and what our initial orbit is going to be to make sure that we don't immediately smash into something. But from that point forward, we rely on the US Air Force, who provide us 3 times a day with an evaluation of any debris larger than 10 centimeters that will pass within a few kilometers of our spacecraft. And that's what we use to make decisions. At the time that we launched, we weren't expecting to ever need to use the propulsion system before the end of our life. The propulsion system is actually really designed to take us safely out of orbit and put us in the Pacific Ocean so that we don't fall on top of somebody's house. But the Chinese had a test of a space weapon system and blew up one of their obsolete weather satellites, and that produced a large cloud of debris. And a couple of years after that, a US satellite and a Soviet satellite collided and produced 2 more clouds of debris. And it's now the case that in the reports that we get from the Air Force, about 70% are from one of those 3 debris clouds. So the problem of having a close encounter or some kind of a collision in space is much, much greater now than it was 5 years ago before those 2 events happened.
Maybe just a question to expand on your dark matter discoveries. I seem to remember you challenging some of existing conventional wisdom around dark matter, and it's caused some fairly intense debate. Could you just summarize that difference in findings and what it may result in to challenge existing dark matter theory?
Okay. So I mean, there's plenty of controversy, so I'll just pick ones that I can think of offhand. There were some initial reports of seeing dark matter that a large fraction of in the Fermi data, that a large fraction of the Fermi community felt were really just simply an artifact of the data analysis. That one of the difficulties with looking for dark matter at the galactic center is that our gamma rays penetrate everything. So we can see right through our galaxy. So that means that if I want to evaluate, before I can say something about dark matter, I first have to understand and subtract that diffuse emission from our Milky Way galaxy. And since we see all of the gamma rays that are produced in the galaxy, you have to imagine a line that goes from us to the galactic center and all the way to the other side. And we have to build a model for how many gamma rays should be produced along that line of sight. And that's extremely difficult to do accurately. So with the initial publications, our feeling was that it was quite likely that we simply didn't understand the data well enough to be able to make a claim about dark matter. Those claims would have put the mass of the dark matter particle quite low in energy, which is consistent with some of the hints that are seen on some ground-based detectors. The more recent observation of a gamma-ray line is much more solid in an analysis sense. Because even if you don't understand the background at all, there's no way in how you can produce gamma rays from the interaction of charged particles moving close to the speed of light with gas and radiation that's going to produce a line. It's going to produce a distribution of energies every time. So in that case, we don't need to worry so much about how to understand the background, and instead can just say, I see a line, this is really a smoking gun of dark matter. So I think that while it is certainly the case that the energy of this dark matter particle will be greater than you expect, and its physical properties are different to what you would expect. When the dark matter particle annihilates, it shouldn't always annihilate just into two gammas to produce a line. You should also have some interaction. I'm getting a little technical here, but you should also have an interaction that'll produce a number of hadrons that then emit gamma rays in a more continuous process and have a continuous distribution. We are not seeing that continuous distribution that you would expect to go hand in hand with a gamma ray line. Theorists can explain everything, and they have, but it's not what we expected ahead of time.
Thank you. You said that gamma rays penetrate everything, but you also said that we can't see them because of the atmosphere. So how can that be then?
Sorry, could you say the question?
You say we couldn't see gamma rays from the Earth because of our atmosphere, but you also see that gamma rays penetrate everything. How come they get struck by the atmosphere?
Well, the quick answer to that is that tells you how unique a place our planet actually is. Our atmosphere, relative to the rest of the universe, is actually very densely populated with material. So if other places in the universe that have a density of matter that's equivalent to the atmosphere would absorb gamma rays, but the fraction of the universe that's like that is so small that we can ignore it.
So that's kind of reassuring, but I think I also heard that if an explosion occurs in our galaxy and we are hit by a gamma burst, it would blow the atmosphere away or something like that, or what would happen?
Yes, if we had a gamma ray burst in our galaxy, it would indeed be quite bad. At minimum, you would probably end up destroying all of the electronics and satellites that are in orbit, because they're not protected by the atmosphere. The side of the Earth that was facing the gamma ray burst would be inundated with a large amount of energy very very rapidly. I don't know if this would actually make the Earth's atmosphere go away, but it would cause serious issues for anybody on that side of the atmosphere. And a few hours later, the rest of us would come around to join them. There have been some hypotheses that the end of the dinosaur era might have been related to a nearby large celestial explosion. Fortunately, gamma-ray bursts have jets, and it's most likely that if there's a gamma-ray burst in our galaxy, the jets would be pointed in some direction that's not towards us. So there's no need to panic.
So you mentioned that one of the most significant discoveries from the Fermi telescope was that the most energetic part of the gamma-ray activity is delayed relative to the start of the gamma-ray burst. What's the significance of that?
We don't know for sure. There's several hypotheses. One, so for a gamma-ray burst, you model it by saying you deposit a huge amount of energy in some small region of space, and then you allow the resulting fireball to expand into the interstellar medium. The jet in this expansion may have both electrons and protons. And electrons lose their energy very quickly. So you can accelerate electrons quite efficiently. They lose their energy quite quickly. So they'll very quickly be accelerated. They'll very quickly start to radiate. Protons, on the other hand, you can accelerate them up to much, much higher energies before they start to radiate their energy away. So if it's the case that the highest energy gamma rays are in fact being produced by a population of protons, then in the fireball, the electrons are immediately accelerated. They immediately produce emission, which is the lower energy emission that we see. And that is a little while later, when the protons have finally got accelerated, they then start emitting, and you might see it being later. That's not the only explanation, but that's one of the hypotheses. Okay, I think that's it. So thank you very much, everyone.